We're finally doing some reading today. So I'm gonna do some math. So we're on 2's complement. I'm picking up where I left off. So here, let us consider the range of values that can be represented as w-bit 2's complement number. The least representable value is given by bit vector 10 to the 0. Set the bit with negative weight, but clear all others. The least representable value is given by bit vector. Having integer value of t-min. The greatest value is given by a bit vector that. Dude, what is happening? Okay, so minimum value is -8, max is 7. You can see that T mapping is a mapping of bit patterns of length W to numbers between T-min and T-max. As we saw with the unsigned representation, every number within the representable range has a unique encoding. It's a principle. So uniqueness is also a unique encoding. We define the function t to b, 2's complement, 2 binary, to be the inverse. It's the unique, okay. Assuming w equals 4, we can assign a numeric value to each possible hexadecimal digit. Assuming either an unsigned or 2's complement interpretation, fill in the following table according to these interpretations by writing out the non-zero powers. Non-zero powers of 2 in the summation. Binary to 2's complement. Binary to unsigned. Oh. So, wait, what exactly do you want from this? Oh, the value. Okay. Wait, 0x1 is just 0, 0, 0, 1, right? Yeah. Okay. 0, 0, 0, 1. This is gonna be 2 to the 0 equals 1, and 2 to the 0 equals 1. 0xb. This is 1, 0, 1, 1. Yep, so this is 2 to the 3 plus 2 to the 1 plus 2 to the 0, which is 10 plus 1, 11. Negative 2, 3 plus 2, 1 plus 2, 0 is 2 plus 1, 3 minus 8, negative 5. So this is negative 5. 0x2, well, this is just 0, 0, 1, 0. 2 to the 1, and then, yeah, 2 to the 1. 0x7 is, what is that? 0x7 to binary. 1, 1, 1, which is 2 to the 2 plus 2 to the 1 plus 2 to the 0. 1 plus 2, 3 plus 4, 7. This is the same thing. 0xc. So that's going to be 1, 1, 0, 0. Yep. 3 plus 2 to 2. 4 plus 8, 12. 4 minus 8, which is negative 4. Alright. First three given ranges of representational number, Umax, Tmin, and Tmax, we will refer to these three special values often in the ensuing discussion. Fuck. 2.14. Where is that? Oh. Unsigned max. This is 2's complementary max, min, which is 128. Alright. A few points are worth highlighting about these numbers. First, as observed, the 2 complement range is asymmetric. Tmin equals Tmax plus 1. Yes. There's no counterpart to Tmin. As we will see, this leads to some peculiar properties of 2's complement arithmetic and can be source of subtle programming. What? Okay, that's actually important to write down. Byte ordering, casting, right here. I'm gonna write that down. Very important. Wait, what is this? Search engine. It used to be my favorite program. Yeah, actually, I want to look at this a little bit. This is building a search engine from scratch, with Python only. Man, I enjoyed this project a lot, but like, as soon as I realized like there's gonna be no users, I just didn't really build it anymore. But I love these kind of projects where it's like an in-depth. There's a lot of things going on. It's a great project for learning. For a portfolio project, not really. Yeah. Anyways, I am going to die. Why is that loading? That doesn't seem very good. Is the server down? Or is this just slow? It's not good if it's this slow. Oh, that's very slow. That's very, very slow. Anyways, that's the church app. Okay. I need to write down the important concept here. Unsigned max and min is asymmetric. Asymmetric. Okay. T min equals T max. There's no positive counterpart to T min. Unsigned max and min is asymmetric. There's no positive counterpart to T min. As we shall see, this leads to some peculiar properties of two complement arithmetic can be the source of subtle program bugs. Asymmetry arises because half the bit patterns represent negative numbers while half symmetry happens because half the bit patterns. Wait, half? Wait, I thought. I'm confused. So it says, I don't know. I don't really understand this part. Asymmetry arises because half the bit patterns represent negative numbers, while half represent non-negative numbers. What the heck? I don't understand this. I don't understand the above. Can you explain? I thought 2's complement meant that the most significant bit, if that is 1, then it's a negative value. In 2's complement, if the most significant number is negative. The part that's confusing is the sentence about asymmetry. Oh, wait. I think it's saying that half the representational numbers can be represented at. Wait, no. Wait, no, I don't. Asymmetry arises because half the bit patterns negative numbers, while half represent non-negative numbers. Okay, so there's. Are you saying there's exactly half? Can you generate all possible bit values with 4 bytes? Is that 4 bytes? Let's see how well these models are doing. Ooh, yes. Okay, there's 15 numbers. 1, 2, 3, 4, 5, 6, 7, 8. Oh my god. That's what it means. Okay. Means that it can represent one less positive number than the negative. Half the bit patterns represent negative numbers, while half represent non-negative numbers. Since 0 is non-negative, this means that there is one less positive number our bits can represent. The maximum unsigned value is just over the twice the maximum 2 complements value. All of the bit patterns that you note that denote negative numbers in 2's complement become positive values in an unsigned representation. Yeah. Where's the bug part? Yeah, right here. This can lead to some peculiar properties of 2's complement arithmetic and can be the source of subtle program bugs. What could the source of... Like, if I had to relate it, reminds me of, like, the array indexing with zeros. That doesn't really matter. I don't think that matters a little. It's a little different. Chelsea, this leads to the particular properties of 2 complements arithmetic and can be the source of subtle program bugs. What could be the subtle program bug here with this, where you can't represent, I'm trying to think. You can have negative 128, but the maximum is 127. Subtle program bugs. Yeah, I don't know. I'm gonna ask chat. I really want to know what the subtle program bugs is. It's also said this. me what subtle bug this could be talking about. It's mainly warning you about bugs caused by the extra negative value, negating the most negative number. For an n-bit signed integer, range is minimum that, maximum that. So the 32-bit signed int. Notice there's no... Oh my god. Is this maximum attack damage? Wait, no. Minecraft. Attribute. It's an attribute. Generic attack damage. I thought it was like 2 million. Wait, the number we see here, is that 2 billion? Yeah, that's probably 2 billion. Yes, this one. No, I swear, I used to have a sword with attack damage of, Nope, no, you're wrong. Dude, it was not kept at this, dude. I swear to God, I swear on everything, it was that. But, well, that makes sense. Now it makes sense why that is. I swear to, like, I swear on everything it was that. Well, this, not the 8. So this is a problem. You might expect y to become positive, but it cannot be represented. It leads to overflow behavior. This one, I like that. Yeah. Int min is, there you go. Alright. This asymmetry arises because half the bit patterns, more on fixed size integer types. Nope. I do not want to read more on this. Also shows representation of constants. Note that -1 has the same bit representation as umax, a string of all ones. What? Oh yeah, why? Wait, why? Why is that? The C standard do not require signed integers to be represented in 2's complement form, but nearly all machines do so. Programmers who are concerned with maximizing portability across all machines should not assume any particular range of representable values. Whoa. Signed int. Do not require. C does not require signed integers to be represented in 2's complement form, but nearly all machines do. Programmers who are concerned with maximizing portability across all possible machines should not assume any particular range of representable values. That is so interesting. Oh my god. Beyond the ranges indicated in figure 2.1, nor should they assume any particular representation of signed numbers. Nor should they assume any particular representation of signed numbers. On the other hand, many programs are written assuming a 2's complement representation. Many programs are written assuming a 2's complement representation of signed numbers and the typical ranges shown in 2.9 and 2.10, and these programs are portable across a broad range of machines and compilers. Many programs are written assuming and the typical ranges, and these programs are portable across a broad range of machines and compilers. So it's basically saying if you want to be really, really precise, if you want to be really precise about all machines, then don't assume we are always using 2's complement representation of signed values, but many programs are written assuming a 2's complement representation. So the typical range can be defined. So what is it saying? So do we do it or not? Like, is it best practice or not? The file limits.hc library is a sets of constants delimiting the ranges of the different integer data types for the particular machine on which the compiler is running. Oh, I guess that's the best. Limits.h. Interesting. Are we using that in homework 1? No. Defines the constant int max, int mint, uint max, describing the range of signed and unsigned integers for a 2's complement machine in which data type int has w bits. These constants correspond to the value tmax, tmin, and umax. The Java standard is quite specific about integer data types and representations. It requires 2 complement representation with the exact ranges shown for the 64-bit case. Figure 2.10. Oh, I'm not going back. Oh, wait. This one? No. Java single byte data type is called byte instead of char. Wait, why? These detailed requirements are intended to enable Java programs to behave identically regardless of the machines. Okay, so Java requires 2's complement representation. Java. Interesting. I want to learn Java actually. In Java, the single byte data type is called byte instead of char. These detailed requirements are intended to enable Java programs to behave identically regardless of the machines or operating system. Intended to enable Java programs to behave identically regardless of the machines or OS running them. To get a better understanding of the 2's complement representation, consider the following code example. We have short, show bytes. Yep. When run on a big Indian machine. The code prints 30, 39 in CF C7, indicating X has hexadecimal representation 0x30 39, while MX has hexadecimal representation CFC7. Expanding these into binary, we get bit patterns. Okay, as figure 2.15 shows, equation 2.3 yields that and that for 2-bit patterns. Oh my god, we just made this. Yeah, it's a very important skill. For the lines labeled A to I in the following listing, convert the hexadecimal value shown to the right of the instructions into their decimal equivalents. No, thank you. Conversions between signed and unsigned. C allows casting between different numeric types. For example, suppose variable x is declared as int and u is unsigned. The expression x unsigned converts the value of x into an unsigned value. Okay. An int u converts the value of u to a signed integer. What should be the effect of casting value to unsigned or vice versa? To cast an int. Well, I'm guessing if you cast the I'm not reading this, by the way. Let's try to guess first. Okay, I think that's a pretty critical thinking skill. So when you cast an int to an unsigned, what I suspect is if like, okay, there's two cases, I think. One, the int value can be represented as unsigned. So meaning positive value, not negative. And second, the int value cannot be represented as unsigned. It's negative. What happens if you cast a negative value to an unsigned variable? Well, I think if it is a negative value, then maybe just take the raw bit representation of the binary of the bits, I guess. So for example, 0x like I don't know. So int value cannot be represented. So like what was once negative and unsigned is 1011 is negative 5. Right, or no, signed unsigned is 11. Signed is negative 5. It'll just be negative 5 to 11. Another thing is if we're going from unsigned to int. Like one case, we are within the max and min, or we just represent it as is. The unsigned max is exceeds. So we take the value will change. That's what I think will happen, but let's see what actually happens. From a mathematical perspective, one can imagine several different conventions. Clearly, we want to preserve any value that can be represented in both forms. On the other hand, converting a negative value to unsigned might yield 0. Might yield 0? It might yield fucking completely something else. Converting an unsigned value that is too large to be represented in 2's complement form might yield Tmax. Oh, what? Might yield Tmax. For most implementations, however, the answer to this question is based on a bit level perspective rather than on a numeric one. For example, consider the following code. Okay, we have a short int of v, which is -1, 2, 3, 4, 5. We have an unsigned short uv. Unsigned short v. Okay. When run on a 2's complement machine, it generates the following output. So u still 1, 2, 3, 4, 5. uv is 53191. I think it did what I said would happen. You went from a integer. You went from a negative integer, unsigned. Went from a negative integer to a positive. Right, so -5 turned into 11. What is in binary? Oh god. In 2's complement? I don't think that's right. What we see here is that the effect of casting is to keep the bit values identical but change how these bits are interpreted. We saw in 2.15 that the 16-bit 2's complement representation identical to the 16-bit unsigned representation. Yeah, I want to see that. I want to see the... Oh my god, I need to fucking poo. Yeah. That was a long shit. My god. Alright. Unsigned. Really large value. Probably turns into a negative, huh? Oh, negative 1. Why would that be negative 1? Dude, that makes so much sense. I've had instances where I used like this exact sequence, right? Like we have, for example, a maximum value, and then you try to like make it into a signed, and it turns into a negative value. Like that makes so much sense. I don't know when I ever had that happen, but yeah, I actually don't know when I had that happen. That is incredibly interesting. That makes so much sense. Holy fuck. 32-bit word size. For 32-bit word size, the bit patterns presenting, oh my god, 4 billion unsigned form with the negative 1 and 2's complement. This is a general rule for how most C implementations handle conversions between signed and unsigned numbers with the same word size. The numeric values might change, but the bit patterns do not. Okay. General rule for how most C implementations handle conversions between signed and unsigned. With the same word size, the numeric values can change, but the bit patterns do not. Let us capture this idea in a more mathematical form. We've defined functions unsigned to binary and 2's complement to binary that map numbers to their bit representations in either unsigned or 2's complement form. That is, given an integer x in the range, the function u2b gives the unique w-bit unsigned representation of x. Similarly, okay, now define a function t2u. Okay, this function takes a number between tmin and tmax and yields a number between 0 and umax, where the two numbers have identical bit representation except that the argument has a 2's complement representation, while the result is unsigned. Yeah, makes sense. Pursuing our earlier examples, I do that? 2.9. 2.19. Where do I put this? How do I even know this? Just be, 2.17. Did I do that one? I did. Wait, what the fuck? These are not the same numbers. Okay, -6. So binary is 1010. It's 10. The bit patterns don't change. It's 10. -5 is gonna be 11. -1, I don't know. Well, -1 be like 2 to the 3 plus 2 to the 2, so 8 plus 4 plus 2 plus 1, which is -1. So 1111 would be -1. What is that in, so that would be 7 plus 8, which is 15. Oh my goodness. Can multiply by 2 and no, I don't think that's a real thing. 12. 1 is gonna be just 1. 8 is gonna be probably just 8. For each of the decimal numbers. Surely chat will be able to do this. 15, 11, 10, 12, 1, 8. Not possible. Oh. Is it because... 8 is not even possible. The relationship we have seen between the 2's complement unsigned number for a given bit can be expressed as a property of the function t to u. Okay. Conversion from 2's complement to unsigned. T to U.
So a chin tuck, what you're going to do is if you're in a head forward position, you're going to bring your head straight back. You are not going to extend up and look at the ceiling. You're not going to look down. Your head posture should stay up and look at the ceiling. You're not going to look down. Your head posture should stay the same, but you're going to give yourself a double chin. You will feel the stretch mainly in your back neck muscles here when you do this, and it's not the most flattering thing, and it's honestly kind of hard to talk when you're doing it.
If you were my patient, I'd say, that's good, but let's actually do this. Work with me.
Well,
there you go.
Well, I'm tight.
You're a little tight there. You need to work on the chin tuck.
I do have a fat neck.
Okay, I want to demonstrate if you're all by yourself and you have a flat wall nearby, you can use it if there's no pictures on there. Put your butt up against their shoulders, shoulders back, and then see if you can touch the back of your head to the wall. Now, I'm doing it incorrectly. This is not a chin tuck. I'm looking up. I want to look straight ahead. Chin goes in, and I'm tight too.
gonna do a workout, and then I have some other tasks I need to do, and then I'm gonna do this quiz. The other tasks are like I'm moving right now, so I have to make sure I have to make sure that I pack my stuff. So yeah, I'll see you guys tomorrow.